Welcome to this lesson. This lesson is about stacks. Before we talk about stack and what's a stack, we need to understand some important concept, which is called abstract data type in software development. So abstract data type, or what we call it ADT, is the way in software development when we build a product, then we just use that product without much details, or without need for much details about the implementation of that module or software. We just concern about the operations regardless of the implementation. So the implementation is hidden, and that's what we have been doing in the previous lessons. For example, when we developed linked lists singly or doubly, after that we will give it to someone else to use them, and just will interact with them through the interfaces at first, at last, remove first, remove last, is empty, size, and those are the public interface or public methods. So that's what we mean by abstract data type. We build some software and we just describe the interface and how others can interact with the software. So the one who will use our software has no need to think about the details of the implementation. And this is one way to reduce the complexity of software development. So that's what we mean by abstract data type. So now let's talk about the stack. Stack is a data structure that holds also a collection of objects, and the main difference between the stack and other structure is about the insertion and deletion or removing. Is in stack is based on the principle last in first out, or what we call it LIFO. So this is the big difference, or the main difference between a stack and other data structure. Now we use such a structure in different applications. For example, when we revised web sites, so if we want to go back, we will get back to the most recent site, and then the next one after that. Also, for example, in text editor like Word, when you type something and you press Ctrl Z to undo something, then you will just do the last thing you did and the one before, and so on. The more important application of using a stack is in the method call in Java or in any other programming language. When we have, for example, method main and main call a method foo, for example, call method bar. What will happen actually that when the processor jump from main to the method foo, it must save all information about the program counter in this method and also about the variables. So it's saved in a stack. Then, for example, here in the foo, the processor will start execute this method, then it finds there is a call for another method. So what will happen, also the program counter in this method should be saved, and also the variables like here k and j, so it will be saved in the memory, and then it will execute bar. When it finished this one, it should jump, it should go back to the foo, not to the main. So if we have such call, then another call, then another call, the only way to go back in reverse is to use a stack. So this is the main application of using a stack structure. Now let's see what are the operations in the stack. We have many operations. One operation is push. So you push an element, that means you add the element on top of the stack. We have pop. Pop means remove, and this remove will return the element on top of the stack, and if the stack is null, if the stack is empty, it will return null. We have top. Now top will just returns the top element of the stack without removing that element. This is very important on difference between top and pop. Here it does not remove the element from the stack, it just tell you what's the top on the stack. Size, well, of course, it will return the number of elements currently in the stack, and is empty will return true if the stack is empty, false if it's not. This is example of a sequence of operations using stack. So for example, assuming the stack initially was empty, has no elements, Then we have bush, we have bush 5, so this bush does not return anything, so the value in the stack will be 5. Then we have bush 3, so the element is 5 3. Size will return 2, which means now we have 2 elements. Bob, it will return the last element inserted or pushed to the stack. In this case it will return 3. Now it will be removed from the stack, so now the stack in this case has only one element, which is 5. Is empty, in this case it's false because it has one element. Bob, again, it will remove the element or the last element in the stack, and in this case, which is 5, and by this the stack becomes empty. So now if we have the method is empty, it will return true. Bob now will return null because stack is empty. Bush 7, so the stack will have 7. Bush 9, it will be 7 9. Top, it will return what's the element on top of the stack, in this, which is in this case is 9, but it will not remove that, so after that 9 is still there. Now if you have bush 4, it means now 7 9 4. Size means we have 3 elements. Bob means remove the last element, so it will remove 4. Bush 6, now it will be 7 9 6. Bush 8 will be 7 9 6 8. If you call Bob now, it will return the last inserted element, which is 8. So it returns 8, and also it removes that from the stack. So those are examples of the operations of the stack. Now how to implement the stack? Here, if we have, like, assuming that we have a stack as an interface, and means we have the main methods in the stack, which is size is empty, bush, top, bob. Now we want to implement them. Here we have two options, or we can do it in two ways. Either we will implement this concept using array, or using a singly linked list. Let's see how we will implement the stack using an array. So we will just have a regular array. We will insert the elements in the array, and based on that we will use a pointer or a reference called, which is just a variable called t, that will hold the index of the last element in the current in the array. So when the size always will be t plus 1, because when t equals 0, that means we have one element which is at number 0. Remember, t indicates or indexes the last element in the stack, or in the array actually now. Okay, when the stack is full, that means we cannot push more elements to the stack. This is an array, so it has that limitation. That means it will reach, in one case it will be full. Okay, so this is the implementation. We implement the interface stack, and here we call this class, or the implementation, we call it array stack. What we have a constant variable, final means constant, it's 1000, and this is the array that will hold the elements of the stack. So it's an array of type E, generic type. Initially t means -1, that means the stack is empty, or it points to nothing. Okay, we have a constructor. This is the constructor that has no arguments. If the user who uses our implementation create a stack using this constructor, so what will happen? Here we have this. The word this here means it will call another constructor that has a one parameter, and it will pass the capacity variable, which is 1000. So this is another constructor here. Okay, it takes capacity, and it just create an array with the size of that array will be the variable capacity. And here, as you can see, this is how we create an array of generic type. We have to create an array of object, then cast it down to the generic type. Okay, size will return how many elements currently in the array, so it returns t plus 1. Boolean is empty, will return t equal -1. Again, if this relational expression is true, it will return, I mean, if it's equal, if t equal -1, that means it's empty. Otherwise, that means it has elements. Okay, the operation push means we want to add, and remember, always in the stack we add at the end. So here we might have an exception, and this is one way to handle an exception. If size means number of elements currently the stack equal the length of the array, that means the stack is full, so we cannot add more elements. So we will just throw this exception, illegal state exception, with the statement stack is full. If not, that means we still have space. So remember, t points to the last element in the array. So what we will do, first of all, we have to increment t to point to a new empty space or slot in the array. Then we will assign this e to this position in the array. Okay, method top should return the element on top of the stack without removing that element. So it check if it's empty. If the stack is empty, it will just return null. If not, it will return data of t. Bob, it's the same as top, but it removes the element. So it returns the element and it removes the element from the stack. Now what we will do here, first of all, it checks if the array is empty, or if the stack is empty, to return null. If not, that means we have some data in the array. So it's the last element is data at t. We will assign it to the variable answer. Then we will put null in that space, in that position in the array, and make t points to the previous element. It's something like this. If this is the array, okay, which represents a stack, and I have a, b, c, so now t will be here. Now if I want to call the method Bob, that means I should return c and make t points to b. So what it will do, it will save this c in a variable called answer, and then it will make null here, and then top should point now to b. So that's why we make t minus minus, and of course at the end we have to return answer. Okay, so now if we go back and see the complexity of those operations, we can find that we don't have any loop here, and each method has a specific number of operations. So that means all operations run in O1 time. And regarding the space, the complexity is On, because we have n elements. The challenge with this implementation, using an array to implement the stack, is that we have maximum size, because it's an array, and this size cannot be changed after we run the code. And also we will reach a case when the stack will be full, and we will have exception. So this is the limitation, or the problem, or challenge with using array to implement the concept of the stack. The other choice is to use single linked list. So we can use single linked list to implement the concept of the stack, and in this case we will not have fixed size like the array. And what we will do, we will just make Bush and Bob as adding element or removing element. If we add and remove the elements from the first, that will be like a stack operation. So we'll use add first to represent Bush, and we'll use remove first to represent Bob. Again, we have top, then we will have first, that you'll just return the element, a last element in the stack, or last element pushed to the stack, and in that case without removing. So first we'll return the first element without removing that element from the linked list. Again, all those operations, remember those operations for single linked list, all of them are running in constant time in O1. So that's good. This is just how we will do it. We have linked list to implement the interface stack that we have before. And here what we do, we just have a list, declare a list, single linked list, and the constructor has nothing, no code. Size will just return list.size. Is empty, will just return list.isEmpty. Bush and element, we just call list add first. Top element, we just return list.first, and Bob, it's remove first. Now as you can see here, we just call the other methods. Here we implement the methods of stack as basically just calling the methods of the corresponding methods of the single linked list. Now what this design is called adapter design pattern, which defines a new class in such a way that it contains an instance of the existing class as hidden field. and we just map the methods between the methods of, for example, here between methods of the stack and the methods of the single linked list. One more thing here is that again we are using the single linked list here as abstract data type. We don't care about the implementation and what's going on when we remove first or remove last, or who we call the other methods. So here we just use them without much concern about the details. So that means we are using the ADT, we are using the single linked list as abstract data type. Okay, some of the applications of the stack is for example, if you want to reverse an array, you just need to push the elements of the array to the stack and then retrieve them back to the array. So for example, if we have an array that has A, B, C, then we will create a stack, we call it buffer, either array stack or linked list stack. So if we assume this is the stack here, I will draw it this way. Okay, what we will do, we will just get the elements. So we have a loop that will go through all the elements of the array, and each time we push them to the stack. So we will push A, B, C. Now we have another loop that will go through the stack and just bob them back to the array. So it will bob the stack. Now the first element will come back from the stack is C. You will put it here, and then you will get B, so it will be put here, and then you will get A. Of course, each time we bob, we remove from the stack, so this will be A. So by that, at the end, you have the array reversed. Another application of using the stack is matching the parentheses. So for example, we have three types of parentheses here. We have this one, and this one. And we want to match the open ones with the closed ones. So for example, if you can see, this is matched if we have many nested types. This is match also, but this does not match because it starts with this one, and this is also not matched because we have this one closed before closing this one, so that's not matched. And this is also not matched because we have only one open parenthesis without the closed one. How to do this? We have here is match that returns true false. It will receive expression contains an expression contains parentheses. Now we have a string called opening that is composed of the three types of the open parentheses. Closing one contains the closed ones, and here what we do, we declare a stack, call it buffer, okay, which is of type linked stack, and we call two-char array, so it converts the expression, the string. Converts the string to an array of characters, and each time we get C, which is a character. So we trace or we track all the characters in that string, but now as a character. We check if that number, if that character is part of the opening parentheses. We will use index of. So index of will return the index or the index of that character in the string opening. We return either 0 or 1 or 2. Or -1 if it's not there. So if it's not -1, that means it's part of the string. We just push the character to the stack. So if we have open parentheses, we push it to the stack. What if we find closed parentheses? So like this one, we'll check if closing.index of C, closing this one, is not equal -1. That means it's either 0 or 1 or 2. That means, okay, the character that we got from the string is now is one of the closed ones. So we need to check if the buffer is empty. That means we don't have a corresponding open parenthesis for this one. So again, it's false. Number of open parentheses should be equal number of closed parentheses. Okay, the other case that we might now what we will do, we will find what's the index of that character in the closing one. So if it's 0, for example, and we bob one element, means we bob one of the open parentheses from the stack. So if that one, the index of this one is not 0, for example here this is 0 and this is not 0, so it's not corresponding to the closed one. That means we have a closed one and we have an open one, but they are not matched, so again we will return a false. If everything is okay, we will continue this loop until we finish the whole string. And now one more condition, we might finish the whole string but we still have something in the stack, which means the number of open parentheses is greater than number of closed ones. So again it won't match if we still have some open parentheses, so we will return buffer is empty. In order to say they are matched, at the end when we finish we should find the stack is empty, so we return buffer is empty either if true or false.